Hi, everyone. We made it. It's the last talk of RustConf 2022. Woo! I'm so excited to be here with you all today. So get settled, get stoked, and all aboard the Rust train. So my name is Julie Wang, and I'm a senior software engineer at Parallel Systems. Parallel was founded back in January of 2020 to decarbonize freight by building an all-electric rail vehicle. Here's the initial software team. You can see we're standing in front of our first rail vehicle in the shop. We were a small team trying to have a large impact. So we went looking for a systems language that was less dangerous than C++, while still offering low-level, safe control in order to control a physical, real-time system. We started looking into Rust and immediately found language features that we liked. So we set off to make a new mode of transport with a new systems language for all of us. My goal today is to tell you about the victories and defeats we've encountered in using Rust across our software stack. But first, let me give you an overview of where software goes on the rail vehicle. Vehicle software runs on our vehicle computer and communicates with firmware on our microcontrollers. Together, they control the hardware systems on the vehicle. The perception application runs on the vehicle computer to detect and react to hazards on the rail. All of this is coordinated by the fleet management software, which lives on remote servers. And all of that code is exercised by our simulation and test software. All the software comes together to make a new way to move freight. Our vehicles are fully electric, fully autonomous, and best of all, they run completely in Rust. In this video, you can see one of our integrated vehicles moving a container around our test site. So let's get into it and talk about what we've built in vehicle software. These vehicles are large electromechanical systems that we have designed and built from the ground up. Here's a picture of the vehicle chassis getting welded. And here's one of our mechanical engineers working with the high voltage battery, which powers the electric motor. You can see a software engineer in the back looking on with great interest as his code gets tested. And here's a render of what the vehicle hardware will eventually look like. Each vehicle has numerous interconnected hardware and software systems. The computers read in inputs from cameras and GPS while accepting commands over Wi-Fi or cellular. Together, they work together to physically move the vehicle around. Building an integrated software and hardware system is challenging. Mechanical and electrical engineers who have designed these systems know the intricacies of how they work and what needs to be turned on and when, but they're not the ones writing code. Software developers can write code, but they need to have a means to accurately and succinctly communicate what they've built to the hardware engineers for their review. As more hardware components get added and more software is written, this complexity can quickly spiral out of control. We address these challenges by organizing our vehicle code into state machines. State machines answer many of these challenges. They offer a clear picture into what the software is doing to the hardware at any given time. Here's a toy example of what the state machine that stops the vehicle looks like. The vehicle initializes into the init state, and each state has particular outputs that are asserted for the duration of the state. In init, no commands are accepted, and the brake is disengaged. Each state, on the very next cycle, the state machine transitions to the idle state. Here, we now accept commands from other state machines to stop. However, the brake itself is not engaged. Upon receiving a command to stop, we transition into the braking state, where the brake is now engaged. When we no longer need to stop, we go back into the idle state, let go of the brake, and that's it. This is just one state machine. Our vehicle is controlled by numerous interacting state machines, each controlling a different hardware system. State machines like this are a common construct used to control hardware systems, and they can be written in various languages. But we found Rust features that made these work extra well. We took advantage of Rust's extensive macro system to implement our state machines. Our macros take care of all of the plumbing work, things like setting outputs and transitioning between states. I want to first show you how easy it is to create a new state machine using the macro system that we developed. To create a state machine, a user calls the states macro with the name of the state machine they want to make. Here's our brake controller. Then, the user defines the states init, idle, and braking, as we saw before. Finally, the user defines the transitions between them, init to idle, idle to braking, and back. And we have additional macros that take care of generating the proper output of each state and define what causes each transition. That's great and all, but you probably wonder, okay, Julie, what's actually going on under the hood? Let's look at what these macros generate. Each possible state gets a struct generated for it. In our case, init, idle, breaking each get their own struct. A trait called transition2 gets auto-implemented for all valid transitions. Here's the transition from breaking to idle. A function called success returns true if it's possible to go from one state to another. Here you can see what causes that transition is if we get a command to stop, we return true because a transition should occur. Otherwise, we return false for no transition. Finally, a from trait gets implemented to actually transform from one state to another. The from function transforms from idle to breaking with nothing magic, it just returns an instance of the breaking struct. Now, let's put it all together in the state machine step function, which is run every cycle. We match against the current state that we're in. If the current state is idle and there's a valid transition to go into breaking, then we transform the current state into the new breaking state. Finally, we set the current state to this new state. I want to emphasize again that thanks to Rust's extensive macro system, all of this code you just saw is auto-generated for every state machine that we write. The developer can focus on what the valid states are and what the correct transitions between them are. You may also be wondering, wait, why bother with all this from trait implementation? We use this transformation from the previous state into the new state to take advantage of Rust's compile time checks. At compile time, we can enforce that only certain state transitions are valid. To illustrate this, let's say we are starting in the init state and try to transition to breaking, an invalid transition. This code wouldn't even compile. The compiler immediately sees that you cannot transition from init straight to breaking. Finally, our macros take all of that state information and for free feeds it into a graph visualization tool to automatically generate state machine diagrams, like this one. This is a snapshot of the actual brake controller state machine in use on the vehicle that goes from init to idle to breaking. You'll notice I simplified the outputs quite a bit. Each time new code is pushed, these state machines get auto-generated. This is huge. This allows our software engineers to point to a state machine diagram that is guaranteed to be accurate with the code that is running on the vehicle. No more trying to match diagram versions against code versions. Whatever is checked into main is what you get. This makes for much easier communication between software and hardware engineers and allows us to visualize the complicated interactions between hardware and software. We've had great success with this state machine framework, and I've used it to define all of our vehicle state machines. The major advantages that we found are it's super easy to make new state machines. Just use a couple macros, and they'll do all the work for you. We are able to enforce the state transitions at compile time, and our code auto-generates highly detailed state machine diagrams. But that's not to say everything is perfect here. These macros can be very opaque. When they're working well, this is fine, but to add additional functionality or to debug, you really need to know what's going on under the hood. This has made it challenging for new developers to immediately start working with our state machines. It can be kind of unclear where the actual code that runs the vehicle lives. We have 10 or so state machines that use this framework, so when you want to add a feature for one in particular, you have to carefully reason about how this would affect other state machines and whether your special case is special enough to warrant changing the overall framework. Finally, while it's great that we don't have to put any work into making the state machine diagrams, they can get pretty big. Some of the important transitions and sort of overall gist of the software can be lost in all of the detail that gets output in the generated diagrams. But overall, we've really appreciated the extra compile time checks and documentation visibility we've been able to achieve with Rust. So we have state machines that control our vehicle, but how do we test them? Rolling around a vehicle as big as ours to test every software change is totally impractical. I've included this picture of two of our vehicles with a spanning structure next to two of our engineers just to give a sense of scale. These things are huge, especially when you consider the container on top. This isn't hardware you can just keep on your desk and run it every time to see how your tweaked software is performing. On top of that, the software we're developing is safety critical. It controls a 10-ton steel vehicle. If your code is incorrect or fails to behave the way you expect, serious accidents can occur. Enter simulation. Our vehicle simulation system exercises the vehicle control software in a variety of environments. We can run our control algorithms without having a physical vehicle present by providing a physics-based simulation of the environment surrounding the software. This lets us do things like stress test our vehicles in bad weather or see how they do on really tight curves. We can also use these simulated environments to perform vehicle design analysis and run randomized scenarios. We visualize and monitor the movement of these simulated vehicles using a combination of telemetry and web applications we've developed. I've included a screenshot here of our fleet management software, which we use to watch things like velocity and location of all the vehicles in our fleet. To simulate the whole world, we had to break things up a little bit. Our simulation components can be logically divided into 3 groups. There are truth models, which simulate the state of the world, and the hardware components. Here we have things like the battery state model, as well as the thermal model. Then there's the hardware abstraction layer, which consists of simulated sensors and actuators that the software uses to interact with the hardware and beyond. And finally, there's the actual vehicle software under test. These nodes have complex interactions with each other. Vehicle software reads in information from the GPS, the battery, and the thermometers. Based on the state of charge of the battery and how hot it is, the control software adjusts the amount of power to the motor and the cooling pump. This, in turn, affects the state of the world, and the state of the world affects itself and the hardware. That's way too much to keep track of. We need a means of organizing these components and calling their various methods in a structured manner. We also want the sim to run as fast as possible, as that allows us to run more tests in the same amount of time. We once again turn to Rust, which allows us to make useful abstractions to build a framework around these distinct nodes, as well as offering fast performance. Our simulation framework is called Conductor, and it organizes this chaos into graphs of interacting nodes. Each node takes in inputs, performs a computation, and produces outputs. As we saw in the previous slide, we have a bunch of different types of nodes to capture the different behaviors needed. We start by making structs for each type of node. For example, a struct for the GPS sensor and the cooling pump nodes. And now let's together try to make a nice interface to interact with these different nodes. Let's kick it off by using Rust traits. We create a trait called node trait that has functions common to all node types. We implement that node trait for the GPS sensor. We have a compute. Where am I? And we also implement it for the cooling pump. How much fluid is pumping? Great. Now we can do things like write a function that can take in anything that implements a node trait. How's the performance, you may ask? In Rust, there's no runtime cost for using generics. This is because the compiler will go through your code and replace all the generic code with specific functions. Then, at runtime, no additional lookups need to be performed. For example, during compilation, any lines that call run computation on a GPS sensor will be replaced with the unique compute function for a GPS sensor. Okay, nice. But what if we have 2 different nodes again, and we want to create a vector containing both of them? Can we do something like this? No, Rust won't let you do that. But we could get around this using a trait object. A trait object created using the dyn keyword allows you to write code where the exact method that you need to call isn't known until runtime. So you can have a vector that contains different types of nodes and call a unique function for each. This looks great. We can hide unnecessary type information and write code to handle all the different nodes that we're going to need in our simulation model. Seems too good to be true. Well, here's the catch. Since we're dynamically figuring out which function to call at runtime, this implementation is significantly slower than the one which uses generics. Is there any way we can get the nice encapsulation of trait objects like we see here with the performance of generics, which we saw earlier? Yes, in Rust, you can cheat and get the best of both worlds. Let's see how you do it. You start off by making an enum that makes a type for each kind of node and contains the node struct as associated data. Then, implement the node trait for the enum type. For each function in the trait, we'll match on the enum's inner type and call the appropriate function for the struct. This gets rid of the need for trait objects, and we still get to use the enum like we would a trait. We wrap up each of the structs with their enum type, and now finally we get that nice vector containing the enum instead of the actual structs. And even better, you can auto-generate all that boilerplate code with a crate called enum dispatch, which gives you custom attributes to slap onto the trait and the enum that you care about. This crate even comes with nice performance benchmarks. When iterating through a vector of 1,000 structs using box object traits and ref object traits, it takes about 5 milliseconds per iteration. When using enum dispatch, our time is 0.5 milliseconds per iteration. This is a 10x improvement. So you might have thought that this section was just about how great Rust performance is, but what I also want to emphasize is how Rust's rapidly growing crates ecosystem has given us the tools to develop a complex physics-based simulation. It seems that Rust has a little bit of everything in crates, allowing us to use a single language to accomplish all sorts of scientific computing tasks. The enum dispatch crate that we've talked about enables us to achieve fast generic performance. Some other crates we're using in our simulation library are the NAlgebra, ND-Array, and LAPACK crates to do matrix math, the ODE solvers crate to solve ordinary differential equations, and PetGraph to make use of graph data structures. Using Rust in our simulation framework has benefited us in a couple of ways. Rust makes abstraction easy with generics, traits, and enums, and you get performance with those nice abstractions. And finally, while not totally complete, there's enough support in Rust crates to enable us to perform complex scientific computing. Here in Rustland, you can have your cake and eat it too. We've just spent some time talking about our vehicle in isolation, but how do our rail vehicles interoperate with other trains on the network? Here's a shot of our test track in California. You can kind of see the rail is the blue and black track path with yellow pins demarcating switches, mileposts, and other points of interest for us and trains on the network. Fun fact, our rail line goes through orange orchards, so we've had a couple incidents where we'd be trying to shoot a video with a quadcopter, and swarms of bees would attack us in our drones. We are first targeting operating our rail vehicles in the United States on mainline rail. Most of the US rail network is controlled through a system called positive train control. Positive train control gets its name from the fact that a train is allowed to move as long as it gets a positive signal to continue. In the absence of a positive message from the central controller, the train will come to a stop. Positive train control was mandated by the US Congress in 2008, and this is the de facto standard across US railroads. So in order to operate our vehicle, we must integrate them with these railroad PTC systems. The way it works is railroad PTC systems will send messages to our fleet management system, which in turn will send commands to our vehicles to move them around the network. There are close to 100 PTC message types defined in the specification, and there are many little quirks in the protocol. Things like numerics, which are 7 bytes long, 5 versions of a single packet type, CRCs on the packet that sometimes don't include certain fields in the packet, fixed length fields with variable length fields just scattered amongst them, structs nested within structs, nested within structs, and my personal favorite, not 1, not 2, but 3 different possible string encodings. Everyone gets a string encoding. We turned to Rust to help manage this complexity. A couple Rust features really helped us out. First off, macros allowed us to embed essentially a custom language within our code to handle all of these packet types. And secondly, as we saw in the simulation section, traits in Rust make abstraction dead simple. Different structs can all implement the same trait and be treated the same by functions. We were again able to implement all of these unique message types with a single set of generic macros, minimizing code repetition and boilerplate. So how do we do it? First off, we defined a codec trait. that encodes and decodes from Rust structs to raw bytes. Then we implemented it for primitive types and derived it for all subsequent types using some macros we wrote. Here's what that codec trait looks like. It contains an encode and a decode function. Next, we implemented a custom-derived macro, which we used to annotate structs. We then defined the structs for every PTC message type, all 100 of them and all their glorious versions. For example, this is the request train ID list 2 struct, which contains some fields for doing just that. All we now have to do is derive codec on the PTC struct like you would debug or clone. And with that, we get the encode and decode functions to make this struct automatically created for us by our macros. Finally, to deal with those 3 unique string encodings that you all got earlier, we wrote some custom attribute macros. Let's revisit that request train ID struct. What I didn't mention earlier is that per the PTC spec, the railroad SCAC field is a 4-byte fixed-length field. We simply add our custom attribute to the field, and our macros will take care of generating the appropriate encode and decode functions to meet the spec. So what has this meant for our PTC implementation? Let's look at a breakdown of the lines of code in the repo. The PTC structs take about 10,000 lines of code to just transcribe from the spec. The codec macro system requires about 1,000 lines of code. And then 5,500 lines of code get generated for us. You can see that the majority of the code base is spent on defining the PTC structs to match the spec. The engineer can focus on getting these right and rely on the macro system to generate all the encoding and decoding functions from there. So in summary, our fleet management system gets packets from positive train control servers and then forwards them on to our vehicles. Our library for parsing these packets makes extensive use of Rust macros. The pros of this are we can focus our engineering effort on getting the structs right. It's trivial to support new message types from PTC, especially as they keep rolling new versions of packet types. But some downsides are that naturally, again, any macro system brings with it layers of indirection and the overhead to initially implement it. Finally, you may be thinking, wait, why didn't you guys just use SerDes? We had a bunch of custom encodings that we had to support, and when we looked at the SerDes API, to be completely honest, we weren't sure we knew Rust well enough to make a SerDes compliant parser to handle all of our edge cases. So we figured the best way to learn was to try, and that anything we wrote would inform future implementations that could perhaps work within the SerDes framework. Overall, we've been very pleased with our PTC encoding and decoding framework, and have been using it to interoperate with third-party railroads. Finally, let's talk about perception, which is the team I now work on. Our vehicles are fully autonomous on the rail with a wide range of operating conditions. What you're seeing here is a video of our deep learning models in action on a variety of train tracks throughout California. We're utilizing various deep learning methods to train and deploy models that can reliably detect and localize hazards around the rail. You can see in this video that we're finding cars, people, bikes, other trains, as well as the rail in front of us. Now you might be thinking, where does Rust fit in here? While we're still using tools like PyTorch to develop and train our models, we use Rust to actually deploy and run the perception process, which is separate from the vehicle process. What is this perception application doing? It takes in raw image data from the cameras and makes them usable. It then does things like save the video to disk to look at later, stream the video to users, and also, of course, run that image data through our models to find the hazards and the rail. We make decisions about whether to slow down or stop. Since we're not a car, we don't have to make any turns. And finally, these decisions are communicated to the vehicle process to perform necessary actions. Now, because we're using NVIDIA hardware as our primary compute, we must use an NVIDIA framework called DeepStream to leverage the platform's hardware acceleration. DeepStream is a series of plugins built in C that move frames of image data from element to element in a pipeline. All of these components shown here would be elements in a DeepStream pipeline. Much of this code is closed source, and only available to use through headers that call into C library files. At first, we thought this meant that we had to write our perception application in C. This would expose us to all of the dangers of a low-level language. Was there a way we could do this with existing libraries was there a way we could use the existing libraries from NVIDIA while still writing the bulk of our application in Rust? Spoiler alert, yes. Otherwise, I wouldn't have put in the talk. Rust makes it easy to communicate with C APIs without overhead, allowing you to leverage Rust's ownership system to provide much stronger safety guarantees for those APIs. We called this project Crabification, which some of you may know as a surprising evolutionary quirk where many types of crustaceans all converge on a crab-like form. For us, this was the process of taking the perception app from C to Rust. The C libraries we needed in our application were DeepStream, the CUDA runtime, and some glib libraries. Rust natively supports linking against these C libraries and calling their functions directly. This is through Rust's Foreign Function Interface, or FFI. The FFI provides a zero-cost abstraction where function calls between Rust and C have identical performance to C function calls. In my mind, this is a killer Rust feature. It allows you to bring in external libraries with no performance overhead. Now that we could call C functions from Rust, we built high-level libraries that provide a safe interface to these functions for the user. The higher-level libraries enforce protocols around pointers, heap memory, constructors, destructors, all the good stuff. Finally, the user now gets to write their top-level application in Rust while still accessing the low-level C libraries provided by NVIDIA. We were able to find bindings and APIs for many of these libraries, so we specifically built out the libraries I've circled in yellow here. We'll start from the bottom with the Rust FFI layer. The first step in all of this is to make your low-level FFI bindings. We made use of the bindgen crate to auto-generate structs and functions in Rust that call into their C counterparts. Let's look at a data structure we had to move over from C. The batch metadata struct, which contains information about the frames in a batch. This struct comes with a create function and a destroy function. Now let's see what bindgen makes for us. First, we get the Rust equivalent of that structure, and it's annotated with representation C, indicating that the struct has the same data layout as C. Next, the extern keyword is used to declare function signatures that Rust code can use to call foreign code. And bindgen creates a signature for the create function and the destroy function. These foreign functions are assumed to be unsafe, so calls to them need to be wrapped with an unsafe block as a promise to the compiler that everything contained within truly is safe. We didn't want the user to have to think about this every time, so we wrap all this in a Rust API. Let's see how we hide our calls to the FFI with an easy-to-use Rust interface for the user. First thing we do is create a struct around the FFI struct that the user can use. We mark it with the transparent attribute. This specifies that batch meta should be treated exactly the same as FFI batch meta. Let's use those C functions with this struct. We define a user-friendly new function that only makes use of Rust types. Next, as we mentioned earlier, we have to wrap our FFI call in an unsafe block. Then we can call that create batch meta function. Some pointer and data manipulation have to happen. I've left this out for clarity. The point of this is that the writer of the crate has to perform all of the checks to guarantee correctness and safety, but this is completely transparent to the eventual user of this API. They don't need to know about all of the terrible, unsafe things you're doing under the hood. Finally, if all goes well, we return an OK. Now, you might have already forgotten about that destroy function. Well, guess what? You probably would have forgotten to call it if you had been writing your code in C. I would have. Let's make it impossible to forget in Rust and put it in the drop trait of the object. We implement the drop function, which in an unsafe block calls the destroy function. Now you don't have to remember to deallocate this memory. The drop trait will do it for you when the object no longer has an owner. OK, phew. Now we've written our API, let's bring it all together and see how that helps our final user application. We are writing a function that transforms coordinates from the image frame into the world frame. We pass variables by value or by reference. We never have to use raw pointers, which can be void. References are always valid. The return type is a result to enforce safer code. This type will emit a compile time warning if the result isn't used, reminding the user to check the result of a function. In C, the best you can do is return an int and hope that the user remembers to do something with an error. The coordinates we want to convert are nested within a couple linked lists per the spec. So using functions from other parts of our DeepStream API, we get all the frames in the batch and go through them. We do the same for every object in the frame, for every piece of user data in the object. This is a standard for loop and iterator combo that should look pretty familiar to everyone. When it comes time to check to see if we have the right type of user data, we can use the if let OK syntax to see if we have the right type. And then we do our math and return an OK. Seems pretty nice, seems pretty straightforward to me. Now, let's see what happens in C. First off, there's no reference types in C, so in the function definition, you have to take in raw pointers to data structures. This is a common source of bugs. You must remember to check for null pointers before you can get to the data. We're using a bunch of pointers, so you gotta initialize them all to null. And remember those nice for loops you had in Rust? Yeah, you don't get those in C. We go through the linked list of the C-style for loop. We could do that a couple times, and in order to actually get the frame data, we have to do a cast from C void to NVDS frame meta. This can be dangerous. We have no guarantee that the data in the frame is in fact of this type. We go through a couple more for loops, and finally, we check to see the correct type to do something with. While functional, as you've probably seen, there's several places in this very short snippet of code where you gotta be really careful about dealing with your raw pointers and your memory. So here's the code side by side for full effect. I don't know about you, but the before code makes me sad, while the Rust version makes me glad. Yay! So using Rust FFI to wrap NVIDIA's libraries has had several benefits and downsides. Perception and vehicle application need to communicate, and we've been able to reduce the interface to a single shared Rust module. Our software development processes, since they're all in Rust, I've been able to share resources and infrastructure with the vehicle software. And as you saw, I believe overall the code base has become safer, easier to read, and has led to faster development. So what are the downsides? Callbacks have been challenging. In our system, you have a Rust wrapper around a C struct that's calling a Rust function through a C callback. It was a bit of a mind bender to get this to work. There's a large DeepStream API to support. I've been approaching this by just adding functionality piecemeal as I need it. And of course, this has been a large project and has required a large overhead to make this crabification effort a reality. It's been a learning journey for all of us as we've built out our software stack using Rust. We initially chose Rust because it's a system language with safe high-level abstractions. In particular, various language features like generics, traits, and enums make abstraction easy while still offering great performance. We found that Rust macros are powerful abstractions that let you eliminate boiler code and create easy-to-use interfaces and documentation. But with great power comes great responsibility. They can be difficult to understand and work within. Rust has numerous crates available to do everything from solving ODEs to serializing bytes on the wire. Rust is a relatively young language, though, so support isn't nearly as complete as, say, NumPy in Python or Simulink in MATLAB, but you can generally get by with what's available. Fortunately, Rust's foreign function interface partially addresses these deficiencies by letting you bring in external C code for no additional runtime cost. So come join us. We're building sweet stuff with rad people, and we want to work with you. Check out our website with open positions at moveparallel.com, and come find me later at the Q&A, or there's no Q&A, at the happy hour. I'll probably get a drink. My email address is here too, so feel free to shoot me a message. And with that, the Rust train has reached its final destination. I hope you enjoyed your trip. Thanks for coming to RustConf, everyone, and see you next year.